tell you about black holes. And I'm going to tell you things that are true, things that follow directly from Einstein's equations, things we're pretty confident about. But they're going to feel wrong. Deeply, viscerally wrong. And that's the point. Black holes are where our intuition completely breaks down. Where the universe reveals that it doesn't care about what feels right to you. It just does what the mathematics says it does. Here's the first thing that feels wrong. If you watch someone fall into a black hole, you never see them cross the event horizon. Never. Not because you lose sight of them, not because they go too fast, but because, from your perspective, time slows down for them as they approach the horizon. Slower and slower. And right at the horizon, time stops completely. You see them getting closer and closer, moving slower and slower, getting redder and redder as their light gets stretched out. But you never, ever see them cross. They freeze at the horizon, asymptotically approaching it for eternity, but never quite getting there. Now you're thinking, okay, so they don't fall in, they just hang there forever. Wrong. They do fall in. From their perspective, they sail right through the horizon in finite time. Nothing special happens at the horizon from their point of view. They just keep falling. So how can both be true? How can they both cross the horizon and never cross the horizon? The answer is that there's no universal now. What's happening now at the black hole depends on your reference frame. From outside, the infalling person never crosses. From their own frame, they cross just fine. Both perspectives are equally valid. Neither is more real than the other. This feels wrong because it violates our intuition about time. We think there's a fact of the matter about whether something has happened yet. But there isn't. Not near a black hole. Time is relative, and different observers disagree about the order of events in a way that can't be resolved. Here's another one. Once something crosses the event horizon, that information is lost. Forever. Irretrievably. No clever trick, no advanced technology, no violation of any known law of physics can get it back. Why? Because the event horizon is a one-way membrane in space-time. Not in space. In space-time. It's not like a physical wall you could break through or dig under. It's a region of space-time where all paths lead inward. Think about time for a second. You can go left or right, forward or backward in space. But in time, you can only go forward. You can't go backward in time. It's not that it's hard or requires a lot of energy. It's that there's no backward in time direction available to you. All your possible paths through space-time point toward the future. At the event horizon of a black hole, the same thing happens with the inward direction. All paths, all possible trajectories lead inward. There's no outward direction, not because something is pushing you in, but because the geometry of space-time itself is such that outward isn't a direction you can go. So once you're inside, you can't get out. Not because you're trapped by a force, but because out doesn't exist as a direction in space-time. All your possible futures lead inward, toward the singularity. This feels wrong because we think of space and time as this fixed stage where things happen. But they're not. They're dynamic. They have geometry. And near a black hole, that geometry does things that our brains, evolved to navigate flat space-time, find completely counterintuitive. Here's where it gets really weird. The singularity at the center of a black hole isn't a place. It's a time. You cross the event horizon. You're now inside the black hole. You try to avoid the singularity. You fire your rockets. You maneuver. You do everything you can to not hit the center. And it doesn't matter. You're going to hit the singularity. Not because you can't escape it in space, but because it's in your future. The singularity is a moment in time. It's not a point you can avoid by going around it. It's a time you're going to reach, like next Tuesday. You can't avoid next Tuesday by going sideways. You avoid it by going backward in time, which you can't do. So the singularity isn't something you hit like a wall. It's something you reach like the end of time. And once you're inside the event horizon, the singularity is in your future as inevitably as tomorrow is in your future right now. This completely violates our intuition about what singularities are. We think of them as points in space, like the center of a sphere. But inside a black hole, the radial direction, the direction toward the center, becomes time-like. It's not a direction in space anymore. It's a direction in time. So when you're falling toward the singularity, you're not moving through space toward a point. You're moving through time toward a moment. And just like you can't stop time from advancing, you can't stop yourself from reaching the singularity. People love to talk about spaghettification. The idea that you get stretched out like spaghetti by tidal forces as you fall into a black hole. And that's true. But here's what feels wrong. For a big enough black hole, you don't feel anything at the event horizon. Nothing. No pain, no stretching, no indication that anything special is happening. You just sail through like it's empty space. Why? Because tidal forces depend on the curvature of space-time. And for a supermassive black hole, the curvature at the event horizon is actually quite gentle. The horizon can be billions of kilometers across. Space-time is curving, but slowly, smoothly. It's like being on Earth. The Earth is round, but the surface is so big relative to your size that it looks flat. Same thing with a supermassive black hole. The space-time is curved, but the curvature is so gentle that you don't notice it locally. The spaghettification comes later, as you get closer to the singularity. The tidal forces grow. Your feet, being slightly closer to the singularity than your head, experience slightly more gravity. That difference grows. Eventually, it's enough to rip you apart. But at the horizon, nothing. You cross into a region from which you can never escape, from which no information can ever return, and you don't even notice. This feels wrong because we expect dramatic things to have dramatic effects. We expect the point of no return to feel significant, but it doesn't. The universe doesn't care about providing you with dramatic cues. Stephen Hawking figured out that black holes evaporate. They emit radiation due to quantum effects near the event horizon. Over incredibly long timescales, they lose mass and eventually disappear entirely. So you think, okay, if I wait long enough, the black hole evaporates and I can escape. Wrong. You're still trapped. The evaporation doesn't save you. Why? Because of that time dilation again. From your perspective, falling toward the singularity, you hit it in finite time. Seconds, maybe minutes for a stellar mass black hole. Much less than the time it takes for the black hole to evaporate, which is more than the current age of the universe for any astrophysical black hole. From the outside perspective, you're frozen at the horizon forever. The black hole evaporates around you over trillions of years, but you don't come out. The information about you gets scrambled into the Hawking radiation in a way we don't fully understand. This creates what's called the information paradox. Information seems to be destroyed, which violates quantum mechanics. We're still arguing about whether the information is really lost or somehow encoded in the radiation. But either way, you're not getting out. This feels wrong because we're used to conservation laws being absolute. Information isn't supposed to disappear. But near black holes, either it does disappear, which violates quantum mechanics, or it's preserved in some incredibly subtle way we haven't figured out yet, which seems almost as bad. Here's a really strange one. As you fall past the event horizon of a black hole, looking back out, you see the entire future history of the universe play out in fast forward. Why? Time dilation again. As you fall in, time outside is running faster and faster from your perspective. You see stars age and die, galaxies collide, the universe expands and cools, all in the few seconds or minutes before you hit the singularity. Except you don't actually see this, because the light gets so redshifted that it becomes invisible. And there are other complications, but in principle, the entire future of the external universe happens during your fall. This means that from your perspective, you fall in and hit the singularity after a finite proper time. But from an outside perspective, you never fall in, you just freeze at the horizon. And the entire future history of the universe happens before you would cross. These aren't contradictory. They're just different perspectives on the same space-time geometry. But it feels contradictory. It feels like there should be a fact of the matter about whether you've crossed or not. There isn't. Here's something subtle. From the outside, a black hole is a region of space-time. It has a size. For a solar mass black hole, the event horizon is a few kilometers across. But from the inside, the interior of a black hole is finite in time. You cross the horizon, and then you have a finite amount of time before you hit the singularity. For a solar mass black hole, microseconds. For a supermassive black hole, maybe hours. The interior isn't a place you can exist in indefinitely. It's not a room you can float around in. It's a finite stretch of time, and then it ends, at the singularity. This is different from any other region of space. Usually, if you're in a room, you can stay there as long as you want. Time keeps going. But inside a black hole, there's a maximum amount of time you can exist. Not because something kills you, but because time itself ends at the singularity. This feels profoundly wrong. We think of space as being persistent. A place might be dangerous, but it doesn't have a built-in expiration date. Inside a black hole does. Cross the horizon, start the timer, and you're going to hit the singularity. Guaranteed. In normal space, motion is relative. If you're moving relative to me, I'm moving relative to you. Symmetric. But falling into a black hole isn't symmetric. Someone falling in sees you staying outside, but you staying outside don't see them falling in. Not really. You see them frozen at the horizon, and there's no way to unfall into a black hole. No reference frame where the infalling observer is actually stationary and the black hole is moving past them. The black hole isn't an object moving through space. It's a feature of space-time geometry. You can't dodge it by changing reference frames. This asymmetry feels wrong. We expect that if someone can fall in, someone else should be able to pull them out, or at least that the situation should be symmetric somehow. But it's not. Falling in is a one-way process. The geometry of space-time doesn't allow for reversal. This one's more conceptual but still feels wrong. Black holes, according to the no-hair theorem, are incredibly simple objects. They're completely characterized by three numbers: mass, charge, and angular momentum. That's it. You could throw in a library, a person, a star, whatever. All that information, all that complexity, reduces to three numbers. The black hole forgets everything else about what fell in. This feels wrong because we're used to objects retaining their properties. If I throw a red ball and a blue ball into a box, there are a red ball and a blue ball in the box. But if I throw them into a black hole, the black hole doesn't become red and blue. It just gains mass. The color information is lost. Where does it go? We don't know. Maybe it's encoded in subtle correlations in the Hawking radiation. Maybe it's truly lost. But the black hole itself doesn't carry that information. It's just mass, charge, and spin. This simplicity is beautiful mathematically, but it feels wrong that the universe would just delete information like that. We expect conservation, tracking, preservation, but black holes seem to violate that expectation. Here's a practical one. You can't hover just outside the event horizon, not without infinite acceleration. As you get closer to the horizon, it takes more and more thrust to stay in place. Right at the horizon, it would take infinite thrust. Impossible. Why? Because hovering means staying at a constant radial coordinate. But as you get closer to the horizon, maintaining constant position requires accelerating faster and faster to fight against the geometry of space-time that's trying to pull you in. At the horizon itself, you'd need to accelerate at the speed of light to stay in place, which is impossible. So you can't hover there. This feels wrong because we're used to being able to position ourselves anywhere we want, given enough force, floating in water, standing on Earth, whatever. It's just a matter of balancing forces. But near a black hole, there's no amount of force that can keep you at the horizon. The geometry itself forbids it. To stay at the horizon, you'd need to move at the speed of light, which you can't do. Despite the name, a black hole isn't a hole, and it's not empty. It has mass, a lot of mass, compressed to incredible density, but you can't see that mass, because it's inside the event horizon. All you see from outside is the horizon itself, which looks like a black sphere. But the mass is really there, inside, warping space-time. This feels wrong because we're used to seeing the things that have mass. A planet has mass, and we see the planet. A star has mass, and we see the star. But a black hole has mass, and all we see is nothing. Blackness. The mass is there. We know because we can measure its gravitational effects. We can see stars orbiting around it, gas falling into it. But we can't see the mass itself. It's hidden behind the horizon. This creates a weird disconnect. We measure the mass through its effects. We know it's there, but we can't observe it directly. It's like having a heavy invisible object. You know it's heavy because you can feel the gravity, but you can't see it or touch it or interact with it in any other way. This is the most mind-bending one. Inside the event horizon, the time direction and the radial direction swap roles. Outside the black hole, time is time-like, and the radial direction is space-like. That means you're forced to move forward in time, but you can move in or out radially if you want. Inside the black hole, it's reversed. The radial direction is time-like, and time is space-like. You're forced to move inward radially, but you could, in principle, move forward or backward in time. except you can't actually move backward in time because of other constraints. But the point is, the character of the dimensions changes. The dimension that used to be space becomes time. The dimension that used to be time becomes space. This is why you can't escape. It's not that there's a force pulling you to the singularity. It's that moving toward the singularity is moving forward in time, and you can't stop moving forward in time. This feels completely wrong. We think of space and time as fundamentally different things. Space is where stuff is. Time is when stuff happens. But in general relativity, they're more similar than you'd think. They're both dimensions of space-time. And near extreme curvature, they can trade roles. So why does all of this feel wrong? Because our intuition is based on everyday experience. And everyday experience doesn't include extreme curvature of space-time. We evolved to throw rocks and run from predators, not to navigate near event horizons. So our brains developed intuitions about space and time that work great in everyday situations and fail completely near black holes. That's okay. The mathematics doesn't care about our intuition. The equations of general relativity describe how space-time curves and how objects move through that curved space-time. And those equations have black holes as solutions. We can't visualize it properly. We can't make it fit our everyday understanding, but we can calculate it. We can predict what would happen, and those predictions match observations. We see stars orbiting invisible massive objects. We see gas spiraling into them and heating up. We've even imaged the shadow of a black hole, the region around it where light can't escape. Everything matches the mathematics. So black holes are real, and they really do have these bizarre properties. Time really does stop at the horizon from an outside perspective. The singularity really is in your future, not in your spatial location. You really can't escape once you're inside. It feels wrong because reality doesn't match our intuition. But that's reality's problem. Or rather, it's our intuition's problem. Reality just is what it is. As a physicist, you learn to trust the mathematics even when it feels wrong, especially when it feels wrong, because the mathematics has been tested and verified and your intuition hasn't. Quantum mechanics feels wrong. Relativity feels wrong. Black holes feel wrong. But they're all correct, as far as we can tell. They're how the universe actually works. And there's something beautiful about that. The universe is stranger than we imagined, stranger than our everyday experience would suggest. And we can figure out these strange truths by doing the mathematics, by following the logic, by trusting the equations, even when they lead to conclusions that feel absurd. That's what physics is. It's not about confirming our intuitions. It's about discovering what's actually true, even when that truth is counterintuitive. Black holes are real. They're out there. And they're exactly as weird as the mathematics says they are. Get used to feeling wrong. That's where the interesting physics lives.